Does this work? Can you hear me in the back? Yes? Okay. Thank you very much, John, and thanks also very much to the organizers for inviting me. I have to say I finished preparing my talk about 10 minutes ago, and I've never given the talk before, so I don't know how long it will last. So feel free to leave if I start going on too long. So the subject of the talk is our attempts to mathematically model large networks by random graphs. And the story begins about 50 years ago with the work of Erdos and Renyi. So they introduced two very similar models for random graphs on n vertices. In one model, we include each of the n choose 2 possible edges independently with probability p. In the other one, we fix some number of edges m that we would like our network to have, and among all subsets of m edges, we simply pick one uniformly at random. Should be saying uniformly down there, so the second independently. So a few observations. These two models are actually quite close. The reason is that if you look at GNP, the number of edges is just a binomial random variable, so it's actually concentrated around this expectation. Another thing is you can think of GNM as being built by adding edges one by one, but as we add edges, we make sure that we have no replacement. And finally, it is not hard to see that if in GNP one conditions on the number of edges, the graph that one gets is uniformly random, so it's equivalent to GNM. Another way, perhaps, to think of these two graphs is you can think of the lattice of all possible graphs on n vertices. So you have the empty graph at the bottom, you have the clique at the top, and the GNM model just picks some particular level of that lattice and picks uniformly inside that level, whereas GNP puts a little binomial over the choice of level and then simply picks a graph uniformly inside there. And if you adopt this kind of this viewpoint, you can realize the following thing. If we look at most interesting graph properties, they tend to be invariant under relabelings of the edges, of the vertices in the graph. And a relatively deep theorem says that if this is true, if you look at any monotone property, the boundary separating the graph set don't have the property with the graph that have the property has to be relatively flat. Okay? It cannot be very slow. So, for example, the sharpest property is the property of having a given number of edges, which is perfectly flat. If we start looking at properties, for example, like having a triangle, it is not quite flat, but because it's any triangle, it turns out the slope cannot be very big. Perhaps the best known such phenomenon of a phase transition in these graphs is the formation of a giant component. So if we think of the edge probability P as being 1 minus epsilon times n for some fixed epsilon, then the expected degree in the graph is 1 minus epsilon, essentially. And in that case, if we look at the connected component structure, we see that all components have size basically logarithmic, and they are trees. A small number of these trees might have a single cycle. On the other hand, as soon as the average degree exceeds 1 by a constant, there is a component of linear size that has a very rich cycle structure. Of course, it's not hard to see that this thing has to be unique. And essentially, the graph around it remains pretty much like it was in the subcritical regime. So I'll start by giving you some idea about how one proves statements like this. So think of the graph as a lottery ticket that you get to scratch off, and there is n choose 2 binary digits, zeros or 1, telling you the presence or absence of each edge. So what we're going to do is we're going to pick a random vertex, maybe vertex 1, and we're going to do breadth first search from that vertex. And we will scratch the lottery ticket off in a need-to-know basis. When we need to know whether an edge is in or out, that's when we do the scratching to find out. So in this particular case, we started at vertex V, and we have exposed all the edges that might or might not be adjacent to V. we've discovered that it's adjacent to 3 vertices. We've exposed all edges that are incident to these 3, and so on and so forth. We've discovered maybe 1 edge inside our tree. And currently, the only edge for which we have not done the scratching is a single edge, and we're about to do so to discover whether it is connected to other vertices in the graph or not. So we do that, and it turns out it has 2 vertices to which it is adjacent. And it's easy to see that the number of children that this vertex is going to have is simply binomial with probability p. And the number of trials is simply n minus I, so this is the ith vertex to be exposed. So this means that we can easily relate this breadth-first search tree to Poisson branching process, because effectively, when you have a binomial where the number of trials is n and the probability of success is a constant over n, the expected number of successes is Poisson. And then the argument kind of goes like something that John mentioned earlier. If the average degree, so the expected progeny in the Poisson process is below 1, the probability that the tree has a certain length drops off exponentially. On the other hand, if the average degree is the expected progeny is above 1, then unless the tree is already pretty big, the reservoir of candidate edges to which each exposure can go still gives us a progeny which is strictly greater than 1. So for the first line, essentially, we show that the branching process is dominated by the Poisson branching process, and in the second case, that it dominates it. And effectively, what happens is that the set of vertices for which the corresponding branching process in some sense survives and lives forever come together and they form the giant component. This last bit, of course, is quite a lot of hand-waving on my part, but at least the fact that there is no giant component before, you can prove just by a union bound. That's why we had exponential tails. And in expectation, at least, we also saw that there should be a giant component when the degree is above 1. It turns out that we know pretty much everything there is to know about this giant component. We even know things like, what's the probability that things are planar? And like I said, the number of vertices in the giant component, the fraction of them, is equal to the survival probability of a branching process whose progeny is Poisson, the average degree. The giant component is actually a very interesting graph, and it has rich structure. So right away, we can see that it has small diameter. This is sometimes referred to as the small world property. And not only that, this diameter is very robust in the sense that if you take a random walk, you will forget where you've started within polylogarithmic, actually just log squared number of steps. I don't know. But this is a fairly recent result. Okay. Yes. Okay. So it's a constant number of years since it was proven. Okay. So what I'm trying to get at is the fact that it has small diameter is not the result of everybody going to a central place and then diffusing back, but in fact, it's actually in a very robust sense. The same robustness is affected by the fact that it's very difficult to destroy this graph. If you try to remove edges, you actually have to remove quite a lot if you were to separate it into 2 large pieces. And another important property that it has is that locally, it's tree-like. So if you take any vertex, even inside the giant component, and you do breadth-first search for any constant depth, you will see a tree, maybe 1 extra edge. So locally, the graph is extremely sparse. Also, like I said, the graph outside the giant component essentially is you can prove that it is isomorphic to the process that results if you simply yank the giant component out, measure the average density, number of edges and vertices in what's left. And this is known as discrete duality. So it's just a bunch of trees. And as we add edges, basically, these trees get absorbed by the giant component. It's worth making a couple of simplifying assumptions. And we will see that this will help us with trying to get our hand on some more numerical sort of features of these graphs. Let's say that we allow replacement, we select edges. So we're in G and M. So we add edges one after the other, but we allow ourselves the possibility. We don't bother with the edges that are already in. We might include an edge twice, so we get a multigraph. It's easy to see that unless we're going to add a quadratic number of edges, the fraction of edges that are going to have multiplicity is vanishing. So in a sense, we don't have to care much. And also, when I say an edge, rather than thinking of it as consisting of two distinct vertices of the graph, allow me to simply choose two vertices of the graph in an independent way. So in principle, I could choose the same vertex twice, giving me a self-loop. That has probability just 1 over n. So again, it is not a big deal. So if we make these two assumptions, then you can think of the process forming the graph as simply 2 times the number of edges uniformly random vertices. So we just select vertices 2m times, and then we say the first and the second are an edge, the third and the fourth are an edge, the 5 and the 6 are an edge. And this gives us a graph. Another way of thinking about the same thing is we have 2m balls corresponding to the endpoints that we're going to throw to n bins corresponding to the vertices. And this is completely uniformly random. So this is an incredibly well-studied studied process. So that's the first ball goes in. It went to this bucket. And then the second goes there, and this is an edge, and so on and so forth. So 1 and 2 is an edge, 3 and 4 is an edge, 5 and 6 is an edge, and so on. So now that we have this mapping onto balls and bins, we can infer a bunch of things pretty automatically just from looking at the study of occupancy problems. The first one is that the degrees of the vertices are essentially independent random variables. The only dependence that they have comes through the fact that their sum has to be 2 times the number of edges. Okay? This is an incredibly weak dependence, so effectively you can think of each vertex as choosing its own degree independently of everybody else just by picking the right Poisson. So jointly, you get a joint Poisson distribution. The maximum degree scales exactly like you know from balls and bins, so it's log n divided by log n. And again, when you adopt this, this point of view of balls and bins, if you ask the question, how long does it take, how many edges are needed before every vertex has degree at least 1, that's a necessary condition, for example, for the graph to be connected, this becomes the coupon collector's problem. You need n log n balls, which means half n log n edges. Now, as the previous picture suggested, already when we have simply n over 2 plus a little bit number of edges, we have this nice giant component, and it keeps absorbing trees. So when we're interested in things like, for example, connectivity, it seems like we're waiting pretty much for all the trees to be absorbed. And this intuition gets borne out in some of the nicest results, at least nicest early results in random graph theory, that basically say, look, assume that you start with n vertices and you add edges 1 by 1, okay? And stop as soon as every vertex has degree at least 1. It turns out that at that moment, with high probability, the graph is going to be connected. So the very edge that brings in that last vertex is actually when you get connectivity. And moreover, the richness of the graph manifests in the fact that in that graph, you can also get a perfect matching. So not only connectivity is happening, but there's so much choice that you can actually hook up vertices in pairs. Maybe there's a single vertex that's left out if this is odd. And if you add a few more edges so that every vertex has degree at least 2, something even more spectacular happens. The graph gets a Hamilton cycle. So this is a cycle that goes through every vertex exactly once. Okay? Obviously, in order to have such a cycle, every vertex must have degree 2. And it turns out that as soon as this trivial necessary condition is fulfilled, you get a Hamilton cycle with high probability. And it gets, in a sense, even more impressive because this Hamilton cycle turns out that it can be found in linear time. Okay, so this is an NP-complete problem. But the graph is so rich that you can find this Hamilton cycle in time which is linear and observe that it's not even linear in the number of edges. It's linear in the number of vertices. You don't even read the whole input before you find the Hamilton cycle. Now, here's another theorem sort of that gives you an idea of the level of control that we have by now on random graphs. It says if you have G and M, so you have some constant times n number of edges, then we can say what the chromatic number of this graph is going to be with very high accuracy. It's one of two consecutive integers. So for example, if the average degree is something like 10 to the 60, then we know that with high probability you need either that many colors or that many colors to color the graph. Okay? So the chromatic number is a very difficult invariant of a graph to compute, yet for random graphs we can nail it very sharply. On the other hand, I don't want to suggest that everything on random graphs is easy. So for example, finding colorings that use so few colors is not so easy. So consider the following trivial algorithm. It barely looks at the input. It just picks vertices, it looks at the neighborhood of a vertex, and it picks a color that hasn't already been assigned to the neighborhood. Okay? The only time the algorithm does anything intelligent, if it turns out that we have k colors available to us, if it turns out that there exists some vertex in the graph, such that in its neighborhood, k minus 1 colors have already been used, so the choice for this vertex is forced, this vertex gets priority. But other than that, nothing intelligent is done by the algorithm. So this algorithm, one can prove it works with high probability when the average degree is about half of what we know is possible. And this has been known now for almost 30 years, yet nobody has been able to improve upon it. So there is no algorithm known for which we can color random graphs for densities greater than what the trivial algorithm achieves. And by known, I don't necessarily mean analyzed. I mean even experimentally, we don't have an algorithm that does this. So this was sort of my way of introducing the by far most popular model for random graphs, the Erdos-Renyi random graph. And the idea was to give you some sense of the level of control that we have over these structures and what kind of techniques are used. Now, something different. So this relates to some work I did while at Microsoft Research about 6 years ago. So this was the time the MSN Messenger data center. So you had the MSN chat client. And when some user came online, it was hashed onto some machine, the machine that was responsible for storing his account. And then we had to notify all his buddies that, hey, this person is now online. We have to send them a notification. And as you can imagine, the job of hashing is to do a nice spreading, and this is precisely what happens. And this essentially was about to bring the network down. So it's not a particularly good implementation. So for reasons I won't go into, it was deemed that what we would like to do is try to partition the graph so that John and his buddies end up on the same machine, or at least most of them. So we had this really big graph, and we would like to partition it so as to minimize network communication. So this is what this graph looked back then, and it really feels like a very long time ago. So the graph had about 110 million vertices, 2 billion arcs. 85% of them were symmetric. If this is a directed graph, so if and this was mostly an artifact of the user interface. It basically made it really easy when someone added you as a buddy to reciprocate. So one of the first findings was that if you ignore the edge directions, then 110 of the 112 million vertices formed a single connected component. So there really was a giant component. And consistently with the Erdos-Renyi graph, the second largest components had 84 vertices. And what was also interesting was that about 1 million people were actually hooked up in pairs. There were 500,000 edges. So people, couples essentially, who used this and didn't use it with anybody else. If you looked at this as a directed graph, then the strongly connected component, so vertices such that there exists a path in both directions, were most of the undirected giant component. There were about 4 million people to which you could get from the strongly connected component, and about 2 million people that could get into it. And then there was another 2 million people sort of who didn't have either of these relationships. If you look at the out degree distribution of such a graph, it falls fairly fast, but nevertheless, heavy tails exist. So for example, there were 18 people with out degree of 20,000. Okay? And 5 people with 20 to 35. And there was 1 person with 48,000 buddies. So as you can imagine, things changed in the software after we found this. So there were hard limits imposed on how many buddies one could have. The point, though, here is that fat tails exist. And this is a plot of the joint in and out degree distribution. So in is that axis, out is that axis, and the vertical is the logarithm of the number of people with that pair of degrees. And as you can see, it's not quite symmetric. So for example, the people that have high in degree is much smaller than the people with high out degree. In other words, there's people who like to observe a lot, but not necessarily that many people who like to be observed. So and remember, this is logarithmic, so the asymmetry is actually quite intense. Perhaps the most dramatic departure of this graph from the Erdos-Renyi model is that if 2 people have a common buddy, then they were about 18,000 times more likely to be buddies themselves. Okay, so there is a tremendous amount of transitivity of adjacency. And I'll show you some pictures of what happens when you pick a random vertex in this graph and you do breadth research just for depth 3. And you will see that it's not necessarily very tree-like. You can see, for example, that very dense graph on the right, and it gets worse. So these are all depth 3. And it's not at all what an Erdos-Renyi graph looks like. In fact, if one takes statistics of those depth 3 neighborhoods, if you look at the number of vertices in them, I don't want to say that this is flat, but as you can see, it is not completely unimodal. So again, if you pick a vertex, and you go 3 steps out, the probability distribution of the number of vertices you will discover or the number of edges you will discover has pretty heavy tails. And if you met someone important at the elevator at Microsoft and you wanted to tell them what the graph looks like, I think the story is basically there is huge variance in connectivity of different users. And you can think of the graph as a superposition of 2 graphs. You have communities like high schools that are pretty densely connected. And then you have international computer science graduate students who basically have friends, different friends all over the world. So we have those short haul links that cause the large clustering coefficient I mentioned, and were very helpful in coming up with good partitions on the graph. But you also have, in some sense, semantically long haul links that cause the graph to be effectively a pretty good expander. So this gives you perhaps some idea of the ways in which one particular large random network, well, I should have said one large network deviates from random graphs. And here is perhaps a longer list of issues with the Erdos-Renyi model. Perhaps the most obvious one is that in real networks, the degrees tend not to be binomial. And perhaps the most prominent deviation is the existence of power laws in the degree distribution. Or sometimes the degree distribution will be exponential, or some other times it will be a power law with an exponential cutoff. So a few more issues are the transitivity of adjacency. That is, the clustering coefficient in this graph is non-vanishing. I'll give you two definitions of clustering coefficients that are pretty similar, but you get the point. The point is there's many, many more triangles than what Erdos-Renyi predicts. Also, Erdos-Renyi graphs are incredibly good expanders. That's not necessarily true of large networks. Some of them are and some of them are not. Particularly in information-type networks, one can find pretty small separators that cut off significant chunks of the network. Also, in a number of networks, there's this notions of assortativity, meaning that vertices have types. And this affects who links to whom. So for example, if you have a food web telling you who eats what, you can imagine. But also similarly, if you look in the internet, you can say that you have three different classes of nodes, end users, ISPs, and backbones. And there's very few links between end users and the backbone, or between ISPs. One particularly simple notion of type by which one can see assortativity is the degree. So in social networks, it turns out that high-degree vertices tend to link to other high-degree vertices more than one would expect at random. But in informational, technological, and biological networks, it turns out that the opposite is true. So here are some very nice statistics that Mark Newman gathered some time back. So here is a table. These are the different definitions. It's the vertices, the edges, the average degree, the mean distance between vertices for which there exists a path. If the graph has a power law, the scaling exponent, then two different definitions of the clustering coefficient, which are pretty similar. And finally, the Pearson coefficient for the degrees of the endpoints of a random edge. So I stick my hand into the network, I pick a single edge, I measure the degree on the left, I measure the degree on the right, that's my sample. I do this many, many times, and I measure the Pearson coefficient. And here are the numbers. As you can see, a number of networks have a power law degree distribution, not all of them. And the clustering coefficient is constant. It's certainly not going to 0, as it does in random graphs. And similarly, you can see that there is assortativity, typically in social networks, assortativity by degree, and disassortativity in the remaining types. So in the rest of the talk, what I will talk about is different ways in which the community has attempted to rectify the problems that Erdos-Renyi graphs have in terms of modeling large networks. I will try to cover broadly those 5 categories, and the idea is mostly to give you a flavor of what's out there. I will not be covering random geometric graphs, for which there is, I believe, a tutorial tomorrow at 4:15. So let's start with perhaps the most glaring discrepancy between Erdos-Renyi graphs and real graphs. That is that the degree sequence is not necessarily binomial. And the way this can be done is by actually simply baking in the degree sequence into the model. So you can say that for each vertex of the graph, we can specify exactly what we want its degree to be. Otherwise, we'll let the graph be random. Or alternatively, you could say, look, I want this fraction of the vertices to have degree 1. I want this fraction of the vertices to have degree 2, this fraction to have degree 3, and so on. So earlier, when I was talking about GNM in terms of balls and bins, we said, well, ball 1 went there and ball 2 went there. So this means there is this edge between the corresponding vertices. And then ball 3 went there, ball 4 went there, and that's another edge. But you can imagine now that if I just do a permutation on my balls, and I just still say 1 and 2 are adjacent and 3 and 4 are adjacent, I get a different graph. Okay? It's easy to see that all multigraphs with this degree sequence are equally likely. There's nothing special about the permutation I choose. And moreover, this is actually true for any degree sequence. The fact that I had a Poisson degree sequence in the case of GNM is actually completely irrelevant. I can simply say, look, here's how many balls I want in that bin. Here's how many balls I want in that other bin. I'll do that for all n bins. Then I pick a random permutation on the balls, and I say 1 and 2 are connected, 3 and 4 are connected, 5 and 6 are connected, and that's it. So this gives me a uniformly random multigraph with that degree sequence. I say multigraph because obviously there is nothing forbidding self-loops or multiple edges. And perhaps a more graphical way of seeing the same thing is we think of the vertices of the graph that we actually care about as the super vertices that carry inside them small vertices, as many as the desired degree for that vertex. And then what we do is we pick a uniformly random matching on the small balls, which we then interpret as a graph in this fashion. And this is how we can get both self-loops and multiple edges. Now, one particularly nice feature is that we can select this matching edge by edge, micro edge by micro edge. We can do this in sequence. So this is our first choice, our second, and so on and so forth. And this turns out to be very helpful in terms of analyzing these graphs. So another thing that's worth knowing is that if the degree sequence is not too skewed, the probability that we will get a graph which is simple is non-vanishing. So what we want is that the second moment of the degree distribution is comparable to the first moment. Okay? If that's true, then the probability the graph will be simple is constant. And it's easy to see that if the graph turns out to be simple, it's a uniformly random graph on that degree sequence, just by the projection of the uniformity into the subspace of simple graphs. So to get a sense of how this requirement behaves, in an Erdos-Renyi graph with average degree d, that quantity, this ratio, behaves like d plus 1. So as you can imagine, the denser the graph is, the less likely it's going to be that we will get something which is simple. But on the other hand, you know, it is not awful. So things like this branching process analysis that I described earlier for the Erdos-Renyi graph generalize, except now vertices have types associated with their degree. So we have a multi-type branching process, but everything else stays the same. And one particularly nice feature is that, in fact, when we choose our matching, prior to starting to choose the matching itself, we can say, listen, there are certain edges that I absolutely forbid. You cannot have those. Okay? And this way, you can pick, for example, bipartite graphs that have a specified degree sequence on the left and a specified degree sequence on the right. And that's exactly how you get ensembles of low-density parity check codes. Now, I mentioned earlier that one of the things we would like to achieve is some kind of assortativity by degree. This is harder to do. It turns out generating such graph is hard, but nevertheless, we can still prove things about them without having an explicitly simple construction by taking a nice generating functions approach, as was done by Newman. I'd also like to give you an example of the type of analysis that one can do in such graphs. So let's say that we're given a graph with some arbitrary degree sequence. In fact, it could even just be the original Erdos-Renyi graph in which we can assume that the degree sequence is Poisson. And we would like to find the largest subgraph of minimum degree k. It turns out that a simple algorithm that achieves this is, look, simultaneously remove all vertices of degree strictly less than k. They have absolutely no chance of ever being a member of that subgraph. And now do it again and again and again until one of two things happens. Either the entire graph vanishes or you're left with a core. Okay, and this is known as the k-core of the graph. And you can think of, in some sense, a slowed down version of this as being, well, let me just do this by removing one edge at a time as opposed to a bunch of vertices. And let me say that an edge is light if at least one of its two endpoints has degree strictly less than k. Clearly, at some point by the first process, one of these two guys is going to be removed, and so the edge will be removed. So I might as well just do this down in this slowed down way. So now we can say, look, put all the vertices that have degree strictly less than k on the left, and all the vertices that have degree k or more on the right at the beginning. And the process that we will do is we will pick, essentially I am drawing these circles. The idea is that I don't really know how many microdots are inside each one of those. These are vertices, but haven't exposed the degree of each one of them. The only thing I know is that those have degree strictly less than k, those have degree more. So what I will do is I'll pick one microdot, I will connect it, it'll either go on this side or it will stay inside here. In either case, I erase these two dots. And occasionally, if it turns out that the connection is to the right, the erasure of this dot is going to cause the vertex on the right to come over to the left. Its degree is slowly going to come down and become strictly less than k. Okay? So already you can see that I am Markovian on a pretty reasonable set. And it turns out I can actually make life a lot simpler. For one thing, I really don't care at all what the degree distribution is on the left, because I'm going to be examining the dots one by one. So I can actually pop them open and have them all appear at once. So I just count the total degree. I have a single number that tells me what's happening on the left. On the other hand, on the right, at least if my original degree is Poisson, it's not hard to prove that since my choices of where the endpoints land on the other side is uniformly random, it will remain Poisson conditional on the fact that it takes the value at least k. So again, I just need one parameter for the left and two parameters for the right. And this is everything I need to write down a martingale for the expected number of like vertices on the left. So this martingale allows me now to model this as a fluid model, take differential equations, and figure out whether this thing will actually hit 0 before something is remaining on the right or not. So I'll show you this with some plots. Time is going sort of this way, and on the vertical axis we have the number of light vertices. On the left plot, the graph is relatively sparser, so the expected trajectory is this red thing. Okay? And as you can see, it never hits 0 before it eats the entire graph. And then the two jagged things are actual realizations. Okay? In one of them, things did go our way, and we managed to eat up the entire graph. In the second one, because the red gets pretty close to 0 at some point, we were a bit unlucky, and the realization hit 0, while there were still a lot of high-degree vertices on the other side. So basically, there was a giant core. On the other hand, when the graph is denser, and the red curve systematically crosses 0, pretty much all our realizations are going to stop far sooner, leaving us with a giant core. And if these plots kind of look familiar to you, it's because they're not really from realizations of the process I talked about. It's actual from decoding of LDPC codes. So the bottom line is a random graph either has a k-core or it doesn't. But when it does, the very moment that that k-core appears, it is completely massive. So think of the experiment of building a graph one edge at a time, and every time after you add a single edge, you ask, do we have a k-core yet? Okay? One can prove that the very first time you add an edge, such that the answer to this question becomes yes, the core is going to contain a majority of the vertices in the graph. So a single edge takes you from absolutely no core to more than half of the vertices being in the core. So this gives you sort of a different kind of phase transition, what a physicist calls a discontinuous phase transition, unlike the phase transition in the size of the giant component. Another nice thing is we can now study random regular graphs. So a one regular graph, random or otherwise, is just a matching. A two regular graph is just a disjoint union of cycles. Neither of these two is very interesting. But if we ask the question, what is a random three regular graph like? It turns out that this is a very, very rich graph. So in particular, with high probability, it's going to be connected. It's going to have logarithmic diameter. It's a fantastic expander. It contains a perfect matching and the Hamiltonian cycle. And this is while every vertex has degree precisely 3. Now, I would really be happy if, in some sense, the one thing that you come away from this lecture is this idea that a random 3 regular graph is a dimensionality monster. Okay, the reason that it can have this incredible richness is because it is an otherworldly object living in very high dimensions. So to make this concrete, consider the following problem. I give you an arbitrary endpoint metric, and I would like you to place its vertices in n-dimensional, let's say for now, Euclidean space, such that if you look at any distance between 2 points in the original metric, it doesn't get bigger, and it also doesn't get much smaller. Okay? So there's a beautiful theorem of Bourgain saying that this is always possible if you allow distortion log n. Okay? And there is an equally nice proof by London, Lillian, and Rabinovich saying that you can't avoid this. There exist metrics for which you really must pay this distortion, and you must pay it in a very strong sense. So for example, if you take a random 3 regular graph, and your metric is the shortest path metric on the vertices of this graph, so the distance between 2 points is their path distance in that graph, then every embedding of this graph in any LP norm, not just L2, not just Euclidean space, is going to distort on average by a factor of log n. So this is as bad as it could possibly be. So it's for every LP, and the average distortion is log n. It's not that there is an exceptional, small, tiny fraction of distances for which things will go badly. Things will go badly in a very strong sense. So I would like to argue that basically random graphs in a degree sequence are too much like Erdos-Renyi graph. Yes, we can bake in the degree sequence, but the fact that the clustering coefficient is small, meaning there is no transitivity of edges, creates these incredibly rich objects in spite of the fact that they don't have these many edges. So for example, if the minimum degree in this graph is 3, the average degree is constant, and no vertex has particularly high degree, it's possible to prove that one can route flow in such a graph proportional to the degree of every vertex with near optimal congestion. So there is a very robust sense in which these graphs facilitate the movement inside them. Now, from a technical point of view, if one really wants to deal with power laws using random graphs in a degree sequence, well, it turns out they're not necessarily the best tool for technical reasons. So there is a vanishing probability of simplicity if the degree sequence drops with an exponent which is anything less than 3, and things then completely also fall apart if the exponent becomes less than 7/6, even if one is willing to tolerate multiple edges. One way to overcome this problem is via a model introduced by Chang and Liu, in which one works with random graphs with an expected degree sequence. So rather than demanding exactly the degree of each vertex, we assign each vertex, if you want, a weight or a potency, and then we say that vertices are joined with probability which is proportional to the product of their potencies. And this gets rid of a number of the technical restrictions for graphs on power law degree sequences. But again, I think that the spirit of this graph is quite similar. Their diameter is logarithmic. Their average distance, in fact, is even better, is log n, if you have high degree vertices acting as hubs. And then later, Chang, Liu, and Wu showed that there is good conductions and a big spectral graph in this graph. So the short version is insisting that the degree sequence obeys what your actual network has for a degree sequence, but leaving everything else to be random, still leaves way too much randomness lying around. So another class of models are random graph growth models, in which rather than saying we'll try to bake in the degree sequence from the beginning, we will actually build the graph step by step and hope that not only it will acquire the desired degree sequence, but because it does in sort of an organic way, it will contain a number of other properties that are of interest to us. So perhaps the first work in this area was done by Price in 1965, who observed that if you look at the number of citations received by different papers, this seems to follow a power law. And in 76, he proposed the preferential attachment model for creating bibliographic networks. So the idea is that this is going to be a directed graph. And right from the beginning, we're going to make the assumption that the average paper cites m other papers. So m is fixed. It's a probability distribution, but it doesn't grow with the size of the graph, which is pretty reasonable. Most people devote about 1 page to the bibliography of their paper. And the sense in which there is preferential attachment is that when a new vertex shows up, when someone writes a paper, the probability they cite another paper is proportional to the number of citations that this paper has already received. So there is some constant D0 saying, look, OK, you might get a citation in spite of the fact that you've never been cited yet. This is how maybe you get your first citation. This corresponds to citing your friend's papers, perhaps. And then what Price showed is that at least for large K, as the size of the network goes to infinity, the probability of having in degree K does indeed scale as a power law, and in fact with a nice varying exponent. So in some sense, a posteriori, we can see that the value of D0 is not very relevant. The model is quite robust, and it doesn't appear in this expression. So this was done in 1976. And then about almost 25 years later, Barabasi and Alder, in a sense, rediscovered a model very similar to this as a model for growth for the web. So you can interpret this again as a directed graph, if you will, except that now the probability of landing, having an outlink to a particular vertex, depends on that total degree of that vertex, not just its in degree. From a mathematical point of view, there's a quite convenient way of thinking about it. The more natural way of putting it is to say that basically you attach to a vertex with a probability proportional to its existing degree. And this paper generated a lot of attention. So here are some of the results that have been proven about it. So it was first really formalized mathematically by Bolobash and Reardon, who proved that its diameter is actually very small. This is a small world graph. But it's also a good it's also a very good expander. It has constant conductance by Mikhail Papadimitriou and Saberi. Volobas and Reardon then proved that, well, this model also has the problem that the clustering coefficient vanishes. So we really don't have transitivity of edges again. And then further, they showed that you only get one particular clustering, one particular power law exponent, alpha equals 3, and that's it. There's nothing you can do about it. And finally, Krapivsky and Redner proved that there is a strong correlation between the age of a vertex and its degree, something which, as was pointed out later by Adamich and Huberman, does not really hold in the web. So the good thing about this model is that it got a lot of people interested in working in this area. At the same time, I don't think that the model itself survives much as a very strong contender for modeling of information networks. And there have been a large number of generalizations and retrofits, but I don't think that any of them really in spirit contradict the properties of the original graph. One thing which is quite nice is that when I described Price's original model, I said the probability that you hook to you cite a particular network is proportional to the network's existing number of citations. So basically in there, I made the linearity assumption. Okay? It could have been that it's some other monotone function of the existing number of citations of that network. It turns out this linearity assumption is not unreasonable. People have made measurements, and they find out that this is pretty much how the world works. A different kind of models for growing networks was introduced in different papers by all these people. So you take the union, that's the names that you get. And the idea is that now when a vertex arrives, it tends to be quite lazy. Okay, think of this as in the old days when actually people had home pages that they built, and moreover, where their home pages, to a large extent, acted as their set of bookmarks. Okay? So in a coping model, when a vertex arrives, it maybe points to a small subset of vertices at random, and then it picks some other vertex at random, the idea being that maybe this is something like a friend, and it literally copies all its outlinks. Okay? And maybe does it with another vertex and another vertex until it has generated enough outlinks to be satisfied. And One nice feature about the model, about this model, is that it's quite rich in bipartite cliques, which was a feature that people discovered early in analyzing web graphs, really was different from Erdos-Renyi graphs. And moreover, it was proven that you do get a power law degree sequence where R is the fraction of vertices that you chose at random. And more mathematical results about this model were later given by Chung, Lu, Du, and Gallus, who also proposed this as a model for biological networks. The idea being that through gene duplication, it is reasonable to believe that the behavior of a certain vertex in the neighborhood will be quite similar to some other vertex. And there are even more models for growth. So Fries and Cooper have a very elaborate model with a number of parameters that combines preferential attachment with copying and moreover allows for vertices to be added and deleted. And in some sense, only Fries and Cooper could analyze it. It's a very technical paper. A paper that personally I like quite a bit more, a paper by Flaxman, Fries, Van Pala, and Vera. And here you have preferential attachment, but in a more geometric sense. So we think of vertices as uniformly random points on a globe. Okay? So if a new vertex arrives, it's literally a random point in S2. And each arriving point is going to connect to M existing points. Now, the probability that it's going to connect to a point at a certain distance is going to be proportional both to the existing degree of that vertex, and it's going to be also a function of the distance. So it turns out, in their first paper, they said, look, when a point lands, there's some critical radius R. It will only connect among things that are in distance within distance R, and among those, it's going to do it by preferential attachment. And what you get is you get a power law degree distribution, and you also get relatively small separators. One thing that is not as nice is that these separators have a very strong geometric flavor. So if you want to actually separate something from the graph, the way you can do this is by taking, for example, a great circle. On the other hand, in a subsequent paper, they showed that if you allow f to be a more elaborate function, not just a 0, 1, you can tune the degree of expansion in this model so that you can tune the sparsity of the cuts that you can find. I think this really depends on the function f. Yes. I mean, for the first model, this is true, but not for the second model. So another way that people have tried to create power laws and degree sequences is on an idea by Carson and Doyle and this notion of highly optimized tolerance. So I'm not quite sure what highly optimized tolerance means, but I can give you a concrete example of a process. So this is a model by Fabrikant, Koutsoupias, and Papadimitriou, and this was meant as a toy model for internet growth. So you have vertices arriving uniformly as points in the unit square, and when a vertex arrives, it tries to optimize two things. On one hand, it really doesn't want to connect to a vertex very far away because it'll have to pay for the copper to actually build that connection. At the same time, though, it knows that after the connection is built, life is going to be better if the network, if the vertex to which it connects tends to be a more central network, a central vertex in the network. So eventually, the vertex plays this trade-off, trying to minimize over all the vertices that are already present some function that's a linear combination of the distance to that vertex and some metric of the centrality of that vertex. You can think of the centrality, for example, as the average number of hops to reach some other destination in the network. And it turns out you get significantly different behavior as you vary alpha. So for example, these are two simulations at 100,000 points. When alpha equals 20, as you can see, the stars, we don't build edges that are very far. On the other hand, when alpha is 4, so we don't care so much about the distance, but we care a lot more about the centrality, the stars become a lot bigger. And the theorem is basically that if you look at the degree distribution, if alpha is big, if the only thing we care about is the cost of copper, then the degree distribution is essentially exponential. You will never hook to someone which is far away. On the other hand, for a relatively large range of values of this parameter, you get a power law in the degree distribution. And then if it turns out that the only thing you care about is the centrality of the vertex to which you connect, the entire graph becomes a star. And it turns out one can get complicated phenomena. Even this, for example, is quite a non-trivial graph to analyze rigorously. And it turns out that one can get into pretty hairy mathematical situations without even trying very hard. So I'll give you an example. So here's a process that stays really, really close to Erdos-Renyi, okay? So in Erdos-Renyi, basically, we put down edges one by one, and at some point we get a giant component. So one could say, in some sense, how inevitable is that giant component? Could it be the case that if I could alter a few edges, maybe I could delay its formation by a lot? So one way of proposing the same thing is to say, look, why don't you throw down 2 edges at a time, and you only get to keep one of the 2, whichever one you like. And your goal is to prevent the giant component from forming. That's it. That's a very, very sort of simple optimization problem. And it turns out that a reasonable rule to follow is to say, I'm going to pick the edge that minimizes, among these 2, E1 and 2, I'm going to pick the one that minimizes the product of the component sizes that it joins. So in standard Erdos-Renyi, it's easy to see that the probability that 2 components are joined is exactly proportional to the product of their sizes. Essentially, it's gravitation. That's the number of possible edges that go in between them. So here, we're trying to forestall gravitation by saying, look, I will pick the less likely of these 2 edges. And what happens is that you get a first-order transition. So you can think of this perhaps as trying to boil something under pressure. You can raise the temperature at which boiling happens, but when boiling happens, it is extremely violent. So similarly here, there is no giant component for more time than what happens in Erdos-Renyi, but when that occurs, the giant component, similarly to the core in the graph, doesn't take off continuously. The fraction of vertices in it does not take off continuously, but it's actually a discontinuous phase transition. Now, there is, okay. So there's not just mathematical complexity that is a problem with these growth models. It turns out that even some of the assumptions that we have been making, that basically the average degree in these networks is independent of time, might not hold. So here's a paper by Leskovich, Kleinberg, and Falutzos. And what they did is they looked at 4 quite important networks. They looked at the archive, the high-energy physics portion of it, the network of patents in the United States, the network of the internet at the level of autonomous systems, and they also looked at an affiliation network between papers and their authors. And what they found is that actually the average degree in these networks goes up with time. So basically we have a densification, which is a feature that is not really modeled by anything I discussed up to now. And moreover, the diameter keeps shrinking as the network becomes bigger. So in some sense, it seems that we have even more work to do than what was already quite hard to achieve. Now, let me talk a little bit about small world graphs. And this is an attempt, in some sense, to capture what is discussed as the elevator version of the MSN messenger graph, the idea that you can think of that graph as consisting of the superposition of 2 graphs. So this was proposed by Watson-Strogatz. And the idea is that we start with some low-dimensional lattice. In this case, the lattice is 1-dimensional. We just take a cycle and vertices, so we sort of have what physicists call periodic boundary conditions. So we just make a cycle. And then we make sure that each vertex connects to all vertices within distance k of it. Okay, that's what we start with. This is what gives us, in some sense, the local density. We bake that into the model. And then what we do is we take a small fraction of the edges that are already present, and we rewire them. So we visit an edge, we flip a coin. If it turns out it's got to be rewired, we randomly change one of its 2 endpoints. And this gives us, in some sense, the long connections. And it turns out that mathematically it's simpler to to just think of the idea, rather than thinking of rewiring, we just say, look, you have this low-dimensional lattice. Why don't you throw some random edges on top and see what happens? How does that change things? So it's not hard to see that if the fraction of rewired edges tends to 0, the clustering coefficient stays high, because most of the edges are these local edges we started with. On the other hand, if everything becomes random, we essentially get a random graph if almost everything is rewired. And similarly, if we don't have any long edges, the diameter is linear. On the other hand, the more edges we rewire, the diameter drops. And it turns out there is an intermediate regime in which we have both clustering and short paths for a relatively large range of P, although mathematically, this has not been very easy to sort of nail down. The intuition, though, for this comes from something that we've already seen, the intuition for this behavior. So I said, start with a low-dimensional lattice and have each vertex connect to all vertices within distance k. So let's make it just really simple. Just start with a cycle on n vertices. So take k to be 1, the dimension is 1. And then we say add a random subset of the remaining edges. Well, what I'm going to do is I'm just going to make sure that each of the vertices gets one extra edge. So basically, every vertex will go from degree 2 to degree 3. So I'll just add a matching. OK? So this is my new graph. And now we can ask, what properties does this graph have? Clearly, this is a 3 regular graph. And it turns out that it's a random 3 regular graph. So this is quite a deep theorem. Remember that we mentioned earlier that a random 3 regular graph has both a Hamiltonian cycle and a perfect matching. It turns out those two can be disjoint. So literally, if you take a cycle and you throw on top of it a random matching, what you get is a probability distribution which is contiguous to the random 3 regular graphs. Okay? So this very much, I think, explains why in small world models with rewiring, there is a very large range of parameters for which we get small worlds. Basically, insisting that we have a matching means that a vertex never has to travel very far to get on a long haul edge. That's it. So if you have this, everything goes away. And I'd like to give a sketch of this very nice theorem by Robinson and Wormald, a sketch of the proof. So imagine we have this, this very big matrix. And each column of this matrix corresponds to a 3 regular graph. Okay, so we take every 3 regular graph that exists, okay, and we create a column for it on n vertices. And then for each of the n factorial possible permutations of the vertices, we write down whether this is a Hamiltonian cycle for this particular graph or not. So this gives us a very, very big 0, 1 matrix. Okay? So the theorem that says, for example, that a random graph has a Hamiltonian cycle with high probability is basically saying, look, if you pick a random column in this graph, so you pick a uniformly random 3 regular graph, it's going to have a Hamiltonian cycle. And if you wanted to basically look at what such a random Hamiltonian cycle looks like, you just pick a column, and then uniformly at random among its many Hamilton cycles, you pick one at random. Okay? The model I described does the opposite. It says, why don't you plant a Hamilton cycle? Okay? I just drew it. I started with n. And then among all 3 regular graphs that contain this as a Hamilton cycle, pick one uniformly at random. Okay? Well, how do you make a cycle 3 regular graph in a uniformly random way? You could just throw a random matching on it. That's the only way you can do it. So in principle, these are 2 very different distributions. Okay? In one case, I first pick a random 3 regular graph, and then I pick a Hamiltonian cycle in it. In the other case, I bake in a Hamiltonian cycle and I throw on top a random matching. Except, though, that the following is true. Imagine that this matrix was perfectly balanced, meaning that every row had the same number of 1s, and every column has the same number of 1s. Then these 2 processes are exactly the same. because what they're both doing is they're both building a uniformly random one for the matrix. So you simultaneously pick a graph and a Hamiltonian cycle for it. Okay? So, okay, well, row balance we get from symmetry. Okay? Having a Hamiltonian cycle cannot possibly depend on the order. Every permutation must be a Hamiltonian cycle for the same number of irregular graphs. What about column balance? Column balance says that, well, all three regular graphs have the same number of Hamiltonian cycle. Of course, this is not exactly true, okay? And this is the hard part of their proof, to establish concentration on this random variable, okay? This is a difficult bit. If you can prove this, you're done. And concentration is, in some sense, a very central idea in this neighborhood, in this area. You can think of a random three regular graph as an incredibly weak shadow of the complete graph. Okay? You go from n edges down to 3. Yet certain properties, like the number of Hamiltonian cycles, manage to remain concentrated in spite of this tremendous amount of thinning. Okay? So this is another way of looking at what gives this graph this incredible combinatorial richness. Now, so we said that a random three regular graph is an incredibly sort of efficient place to be. Traffic flows perfectly, there's no congestion. Pretty much everything is nearby, the diameter is log n. So if you think of it as a place, you could say, well, how would you like to live there? Okay? And if you're from a small town like Ithaca, you can find this high-dimensional beast a very disorienting place. Okay? You can say, yeah, okay, maybe everything is nearby, but how am I going to be able to find these short paths? Okay? So this is some very nice work that John did on navigating small world graphs. So he said, again, let's take a lattice exactly like before. This time, it's a bit easier to illustrate in 2 dimensions. We're still going to add one additional link per vertex, except that this time the destination of the link is not going to be uniformly random. The probability that I have a long link is going to be smaller than the probability that I have a short link. And in fact, the probability is going to be inversely proportional to the distance between the 2 vertices, with some particular exponent that I'm going to tune. So for example, if I take this exponent to be 0, well, the destination is uniformly random. On the other hand, in this case, if I take the exponent to be 2, my destination is going to be at a uniformly random distance scale, meaning it's going to be at distance 2 to the I for some uniformly random I. And what John showed is that in such graphs, there exists particularly one nice value of R for which you can find paths very efficiently griddily. So the algorithm we're going to use is, when I'm at a vertex, I'm going to take out of the 5 possible links the one that gets me closest to my destination. Okay, I don't care if it's a short link or a long link, that's what I'm going to do. So all my routing is going to be done by local information. And the theorem he showed is that if you pick this R just right, this will work. Basically, if you make R to be too small, you can't aim. If you make R to be too big, there are not enough long enough edges to be able to achieve what you want. A few observations about this setting. This works for any constant dimension. So it works for the cycle that I mentioned earlier. It works here for d equals 2. Observe that short paths exist for all R between 0 and d, except that unless R is equal to d, they're very hard to find. Okay, so it's not really that we have done away with the expander nature of this graph. And if you say that the distance between 2 vertices is their distance under greedy routing, this is still a terrible embedding. Okay? But on the other hand, it does get you from every place to every other place within distance log n. Effectively, if you do greedy routing, it could be that while you're headed this way, your next door neighbor right behind you might have a direct link to your destination, and you'll never know. Okay? So your distance is actually very, very small, but you can never find out. And finally, if you look in terms of realizing this graph, the savings that we got by making long edges less frequent is not that dramatic. So for example, in the one-dimensional case, if you think that adjacent vertices have distance 1, then an average edge has length theta of n. Here, it's just theta of n log n. So it is still a very expensive graph to build. Finally, I'd like to say one last thing about embeddings. And again, this is the union of a few papers. If we're willing to tolerate that there is a constant fraction of the distances that we're going to distort arbitrarily, then actually embedding is possible. Not only that, but it takes a particularly nice form. For each vertex, so you pick a constant number of beacon vertices, and for each vertex, you just measure its distance to these beacons. And it turns out the doubling dimension of the underlying metric is what is really key. Doubling dimension being relatively low for most networks of interest. How much time do I have? 10. Okay. All right. Order 10 is what you said? Okay. Let me talk a little bit about exponential random graphs, or P models. So here the idea is to take the moral high road. Okay, we will do things right. We will be like statistical physicists. Okay? So we're going to fix the number of vertices, but then for every other feature of the graph, we're going to call this an observable. So we can have observables like the number of edges, the number of triangles, the number of vertices of a given degree. And we're going to have a Hamiltonian that tells us how desirable is a particular graph by looking at how close it is to each of these target values for these quantities. So for each of these observables, we have a target value t sub I, and then we have a strictness about how much we care as to whether we're close to the target. So basically here, big numbers are bad, big negative number. So the ideal thing is 0, right? We hit each one of the targets on the head, then the energy is 0. Otherwise, it's minus some number. The bigger the number, the worse off we are. So we would like to sample graphs from all graphs on n vertices with probability that it's proportional to E to some global inverse temperature that we have, how strict we are in our sampling, times the value of this Hamiltonian. Okay? So for example, if you make lambda to be very big, you can put all the measure on exactly the graphs you want. On the other hand, if you take lambda to be 0, all graphs get essentially the same probability. I don't think it gets much more elegant than this. And you know, now that we have our nice statistical mechanics setting, we just take the standard route. We apply Metropolis Hastings. We take the set of all graphs. We define some ergodic move set on this set of graphs. We'll see a very simple one shortly. And then we just do Metropolis Hastings. If something lowers the energy, we always take it. Otherwise, we accept it. But you know, the higher the energy that we have to go up, the less likely we are to do so. So everything is completely standard. And moreover, the set of moves that one needs is very simple. If you don't fix the number of edges, so you can have things like deletions of edges and insertions of edges, and then you just need one more move set, and one more move, and you're pretty good. And I'll just show it with only 2 edges, just to get rid of the noise around it. So if you have these 2 edges, and you replace them with these 2 edges, that's it. Now everything is ergodic. And notice that this is a particularly important move because it keeps the degree of every vertex constant. Okay? So this, for example, allows you to walk on graphs with a particular degree sequence without inserting or removing edges. Okay, so we have everything, basically. Except this is pretty much intractable. There's nothing really useful that you can do with this mathematically. It's too complicated. There's one exception that proves the rule, which is, look, if edges not sharing endpoints are uncorrelated, then maybe you can prove something. This is known as Markov graphs. But you know, the whole point here was to actually create correlations between edges. If we have correlation decay at distance 1, then you know, we sort of throw away the baby along with the bathwater. Now, experimentally, this achieves quite fast convergence, or at least what we think is convergence. It looks like it has converged because we can't prove it. Except it doesn't necessarily converge to what we were hoping for. Okay? So imagine, for example, that you have some particular number of triangles in mind that you would like your graph to have. Well, it turns out that the probability of this graph on the left, where I pack all the triangles inside a fork-leak, leaving a tremendous amount of entropy for the rest, is much, much greater than taking those 4 same triangles and spreading them around. Okay? In other words, there are many, many more graphs that have precisely 4 triangles of the form a clique plus do whatever the hell you want with the rest than they are of the other kind. Okay? In other words, those entropy trade-offs do not necessarily resolve in the way that we do. So one has to handcraft the energy function even more. Finally, I will talk about kernel random graphs, and this is something that I like a lot. I will barely scratch the surface, though, because there is a very nice talk coming up on this tomorrow. So the basic idea is that we take an n by n matrix of numbers between 0 and 1. So this is some kind of deterministic matrix, think of it for now. So n by n, so it's going to generate directed graphs. And we round each entry of this matrix independently, okay? So we go from a matrix of real numbers to an adjacency matrix by randomized rounding. Okay, if an entry is p, we set it to 1 with probability p, otherwise we set probability 0. So for example, you can think of G and P as coming from the matrix where all the entries are equal to Q, and we say that an edge exists if either one of the 2 directed edges exists. Okay, so G and P is a case in which this matrix P has rank 1. Okay? Some early applications of these matrices were to create random instances of optimization problems with hidden solutions. So for example, imagine I take my n vertices, I partition them into 5 sets of roughly equal size, and then I create a uniformly random graph, except there are no edges allowed to be inside each of these sets. So this is baked in to be a 5-colorable graph. The question is, can you find the 5 coloring? Okay? And as you can imagine, the larger Q is, the easier the task gets because you get more and more hints. And this was also a very nice testbed for spectral algorithms. One thing which has come up recently is that it turns out that if in random graphs certain properties are actually typical for the graph, then explicitly hiding them does not really change the distribution. Okay? And this is a different way of creating one-way functions out of random objects. Now, I think I will skip the Kronecker graphs. So the Kronecker graphs, just in one sentence, is a particular mechanism for constructing this matrix P that is recursive. You start for a very simple matrix, and you just take the Kronecker product with itself, and it exhibits densifications, which is one of the nice properties that it has. But the part that I really like is this idea of thinking of P as the gram matrix of n random objects. Okay? So this matrix P is going to be random itself. So we first create a random matrix of probabilities, and then we randomly round this matrix. There was some early work on this was done by thinking of P as the product of 2 n by k matrices, one that captures sort of, in some sense, the hubness of each page on the web, and a different one that captures its authoritativeness. And then you take the inner product of these two, and it gives you how likely it is to get a link from A to B. More generally, this is a more recent work by Bolobas, Jansson, Riordan, and also Mihail and Yang. We have IID objects, which more often you can think of as just vectors in some low-dimensional space from some probability distribution. And then Pij is simply the value of the kernel function between vector i and vector j. So you can think of the kernel as being the inner product, that was in the previous example, but this can be a general kernel function. The only thing you need, is bounded support on the distribution for the xi's, plus some sparsification factor. Okay, because this kernel function is always going to have values, between 0 and 1. We don't allow it to depend on n. We sparsify the graph by this g of n. So I think what's particularly nice about this setting is that this double randomization allows us to achieve local density without hard correlations. So for example, if you think in random geometric graphs, you have the first randomization. It puts the point on the plane, but then you have hard constraints. Okay, by the triangle inequality, if this is connected to this and this is connected to this, the distance between these two cannot be more than something. Whereas here, the random placement in a low-dimensional space creates correlations in the values for Pij, but the rounding allows us, the independent rounding allows us to treat things a lot better on a mathematical point of view. So Milena will we'll talk about this tomorrow at 5:20. And to conclude, I think it's quite hard to strike a balance between realism and mathematical tractability for these models. And one reason is that different effects dominate different domains. Arguably, the hardest thing to deal with is conditional dependencies, this idea that if two people have a common friend, then the probability that they are friends themselves goes up significantly. And this last idea of speaking of random kernel graphs seems to be sort of a nice way of capturing most of the benefit of having local density without necessarily having to deal with the mathematical difficulty of hard correlations. That's it. Thank you.